everybody's heard the Doppler effect. But did you know that you need to take the Doppler effect into account if you want to communicate with a spacecraft? I've got here a Doppler ball. It's designed to illustrate the Doppler effect for sound. Of course, the Doppler effect works for all types of waves, electromagnetic waves as well as sound. But this is going to produce a sound with a constant frequency. It's the source of the sound, it's sitting here in the middle, and you can imagine the sound waves radiating out, getting further and further away, just as you would see ripples on a pond if you dropped a stone in the middle. If this source of sound stays constant, stays still here, then each distance from one wavefront to the next, to the next, to the next is going to be constant. We've got a constant frequency. But now imagine if the source of the sound is moving. If the waves are spreading out like this, and my source is moving as well, then if it moves in this direction, it's going to catch up with the waves in front of it. And the distance between one wavefront and the next is going to reduce. On the other hand, looking behind the source, the waves fronts are going to have a bigger distance between them. On this side, the wavelength is shorter and the frequency is higher. On this side, the wavelength is longer and the frequency is lower. Let's see if we can see that in action. I'm going to turn on the sound and now I'm going to spin it around. As this comes towards the microphone, you should hear the sound pitch go up. And as it comes away from the microphone, you should hear the sound go down in frequency, a lower note. Up and down as this ball goes away and towards the microphone. So there's the Doppler effect in action. So what's true for the Doppler ball is also true of satellites in their orbit around Earth. Sometimes they're coming towards the base station and sometimes they're coming away from it. As they approach the base station, the frequency of the waves that they're emitting is going to become shortened, the frequency is going to be increased. And as they're moving away from the base station, the frequency of the waves they're emitting is going to be stretched, the frequency is going to decrease. If you're going to communicate effectively with them, you've got to take that into account. The Doppler effect becomes even more interesting when we start to look at light and other electromagnetic radiation that reaches us from distant stars and indeed distant galaxies. Imagine that this wave here is some light that's reaching us from a distant star. You can see the wavelength of the wave here. We've gone from one peak to another peak. And this is what we would expect the frequency and the wavelength to be. But it's not. When we measure it, what we find is that the wavelength has become stretched. The frequency has decreased, and that's because the star is moving away from us. It's actually travelling further away, it's travelling away from us at a fast speed, and we've got the Doppler effect going on. The wavelength has increased quite significantly. In fact, it's shifted from the normal visible spectrum towards the red end of the spectrum. This is a phenomenon known as red shift. What's even more interesting is that we find a huge red shift when we start to look at distant galaxies. And what we've discovered is it's not just that they're moving away from us. In fact, the whole universe is expanding and causing this effect. We're really privileged today because we've been allowed to carry out this demonstration in the European Space Agency's test facility. Just take a look around. It's in this room that spacecraft can be tested and checked out before they go into space. It's designed to absorb every single radiation that hits the walls. As the waves hit the cones, they are absorbed. There are no echoes in this room whatsoever. Let's just hear it one more time.